Hello, YouTube world. We're back again with another episode of Aerospace Engineering with Brian McNulty. That's me, Brian McNulty, and today I'll be picking up where we left off on the isentropic processes and the adiabatic processes regarding the fluid flow through rocket nozzles. In this video, I'm going to explain why these fluids are flowing in this strange manner as we discuss these supersonic velocity flowing fluids. As they flow through a diverging nozzle, they continue to accelerate. And so we're going to take a mathematical look at why that is today. Let's get started. The first couple of equations that we will be looking at today are going to be thermodynamic equations, essentially stating that the isentropic process is defined when the system's entropy remains constant. And the second one states that the temperature of a system times the delta S, or change in entropy, of that system is going to be greater or equal to the heat gained by the system. Okay, so that's a lot to say, but it makes sense. Now, if the process is reversible, the equality sign changes, and in fact, the temperature in Kelvin multiplied by the change in entropy is actually equal to the heat gained by the system. So take a moment to think about that. It can be confusing initially. These are difficult concepts. So from those equations, it tells us two things. It tells us that the process is occurring in a closed system, which we defined in an earlier video as being an adiabatic process. And then we also determined that since there is an equal sign and the product of the temperature and the change in entropy is equal to the heat gained by the system, then we have ourselves a reversible process. Now, not to beat the dead horse or anything, but that indicates that it is an isentropic process by definition because it is adiabatic and reversible. All right, so now let's have a word about enthalpy. Now, what enthalpy is the internal energy of a system plus the pressure times the volume. Now, you see capital H right here is going to be your enthalpy value. U is going to be the internal energy of the system, and then you're going to add the product of the pressure and the volume together. And then so dividing all of this by the energy mass of an ideal gas, we get what's called the specific enthalpy, where this little u is going to be your specific internal energy, and VSP is going to be what's called the specific volume. Notice that the specific volume is actually just the inverse of density. Okay, so that brings us to our next point. We know as the flow of the exhaust gases are accelerated through the converging nozzle, that the kinetic energy of that gas is changing as well. But since we know that the process is adiabatic, meaning that it's closed off from energy transferring into or out of it, then there has to be a trade-off. And this was discovered by the famous scientist Bernoulli, who coined the famous Bernoulli principle. And he discovered that the specific enthalpy plus the kinetic energy of these gases must be a constant, since there has to be a trade-off. There has to be a trade-off because the system is closed. And so that can be mathematically described as follows. You can get a better look at what I'm talking about when you can see the equation. So the H is going to be the specific enthalpy of the system, and the 1/2 V squared part is going to be what's called the specific kinetic energy. You can see that if one of those values goes up, the other one has to go down, and vice versa. In other words, they have an inverse relationship. So this is essentially telling us how the flow happens down the converging nozzle, where it reaches the throat of the nozzle and then goes through the diverging nozzle. Now the mystery is, when it starts going through the diverging nozzle, why does it continue to accelerate? So we're going to take a look at some of the mathematical concepts behind this phenomenon. So before we even start talking about how this is going to happen, we need to consider the speed of the fluids in the rocket nozzle. So a perfectly designed nozzle will make it so that the fluid flow ends up being exactly the speed of sound at the throat of the nozzle. And hopefully this occurs without a shock wave being generated. So that's important, and that kind of describes what a perfectly defined rocket nozzle is. In order to do what we said we were going to do at the beginning of this video, we're going to have to consider the speed of sound in different gases. And in this case, the gases that we'll be considering are the ones being expelled by the rocket, or in other words, the exhaust gases. Okay, so here you have the equation for the speed of sound. You might have thought, well, isn't it just, 600 miles an hour or whatever they always say it is, Mach 1? Well, yeah, it is Mach 1, but the speed of sound depends on also the medium, as you can see from the equation, the medium at which its waves are being propagated through. And so, as you can see from here, that what is going on is that the speed of sound is equal to the square root of gamma RT. Now, gamma is going to be a ratio, and that ratio is the heat capacity at a constant pressure. And it's the ratio, so it's the ratio of the heat capacity of constant pressure to the ratio of the heat capacity at constant volume. And these are represented by C sub P and C sub V. I didn't write that down, but we're going to get to it in a second. R is going to be the ideal gas constant, and T is obviously going to be your temperature measured in Kelvin. So really what this means is that you can't even calculate the speed of sound until you know what gas you're going through. And that means that you can't calculate the Mach number, because the Mach number is only velocity divided by the speed of sound through whichever medium you're talking about. In this case, remember, it's not the air that we're breathing. It is the exhaust gases that are coming out of the rocket nozzle. So let's take a look at that equation, and you'll easily see that this is a pretty simple part of the calculation. All right, so far in our supersonic flow equations, we have the one for the speed of sound in different mediums, and then we have the one for Mach number. That's what that variable on the left is there, and as you can see, just like I said before, all it is the velocity of the gas divided by the speed of sound in that medium, which is the rocket gases. Okay, so good so far. Pretty easy. Now for you math heads out there, we're going to get into some calculus right now, as we do when we talk about mass flow rate. So we know that the mass flow rate is going to be constant through the rocket nozzle. The thing that's changing is going to be the area of the nozzle as the flow flows through it, which will in turn change the velocity. But the mass flow rate will stay constant. So what we're going to do is we are going to basically take a mathematical look at this and describe it with, well, mathematics. All right, here it is. Okay, so as you can see, the mass flow rate thing, it might look like a lot initially, but I'm going to talk through it right now. So basically, what we have is the mass flow rate, which is, so the mass flow rate through a converging nozzle is going to be equal to the density times the velocity times the area of that nozzle. And we talked about that. The mass flow rate was going to be constant, which is why I wrote that there. So what we're going to do is we're going to take the derivative of that whole thing, and we know that a derivative of any constant is going to be 0, and then just taking the derivative of the rho VA part, we end up getting this second line here. Now what we're going to do is we are going to take some steps to simplify this equation. So right now in the third line, we're going to divide by rho VA, which is going to give us this nice looking thing in the fourth line, d rho divided by rho plus the quantity dV divided by V plus dA divided by A, and that's going to equal 0. So we have an equation here, and we will revisit this once it matters. Now you're probably thinking, you know, oh man, this is like becoming a lot. You said this is going to be not that bad. Well, bad news, we're not even close to done yet. So now what I'm going to do is introduce to you another equation, and this is an equation for isentropic flow. So check this one out. Okay, so I present to you the isentropic flow equation that we will be discussing. So basically what this says, just take a moment to look at it. You can see that we start off with the change in pressure divided by the actual pressure is equal to this heat capacity ratio between pressure and volume multiplied by the change in density divided by the actual density. Now, because P equals the square of the speed of sound in that medium, it also equals gamma RT. That's from our previous definition. I believe one of the first equations we wrote down in this video. Now, going from line 1 to line 2, all I did was I divided the pressure out of the left side of the equation so that we put it on the right, and then we do some simplifying with our new definition of pressure, which is going to be gamma RT. And when we substitute that in, we end up getting all forms of this equation. I just wrote down a bunch of different forms, but the final form that I'll leave it in here is in terms of the speed of sound, or A squared, A sub 0 squared times dP equals, d rho. That's not a P, that's a rho. And then it equals the change in pressure. All right, so now we're going to take that isentropic flow equation and we're going to express it so that it describes the flow of the fluid in terms of the flow velocity, the Mach number, and the effective cross-sectional area of the nozzle. So I guess without waiting around, let's just hop right into that. And would you take a look at that thing? Not too bad. I'll explain it. So basically what's going to happen is we are going to express the conservation of momentum of a gas as such. And so since, and I'm just looking at this here, since the change in pressure, or the negative change in pressure, is going to be equal to the negative square of the speed of sound times the change in the density of the gas, we can rewrite the equation this way. Then multiplying by V over V, or simply just 1, basically just converting the equation, we end up getting this down here. And I'm not going to say all that, but these are what the equations are. And so once you do that, you end up getting, oh, well, something interesting has happened here. So because the Mach number, like we discussed before, equals velocity over the speed of sound, then that means that the negative square of the Mach number times the change in velocity, or the acceleration of the fluid, I guess, is going to be equal to the change in density over the density. Now, from an earlier equation that is in this video, regarding the one that we set the constant equal to 0, so basically that's what that is right there on this line. And then simplifying it all the way, we get this equation. And this, like I said, is going to describe the fluid flow in relation to the flows, the velocity of the flow field, the effective cross-sectional area, and the Mach number that you're given. So a Mach number that is greater than 1, then that means that a positive area change in the nozzle will indicate a an increase in the velocity. So for Mach numbers that are less than 1, if the area change is positive, then the velocity change decreases. So the velocity change is negative. And so that's kind of the whole point of deriving all these equations, to kind of determine if the fluid velocities are at, below, or above the speed of sound in these particular exhaust gases. So essentially the flow is going to, the subsonic flow is going to break the sound barrier at the throat of the nozzle. That means that at the throat of the nozzle, the fluid should be at what we just defined as Mach 1. And so I think I'm going to stop right there. But I hope you enjoyed the video. This is a great look at rocket science and the more technical aspects that can come of it, and the concepts that happen inside of the field. It's really astonishing. And so that was a lot to take in. I would encourage you to watch the video several times, and also download the Introduction to Rocket Science and Engineering PDF by a rocket scientist by the name of Travis Taylor. So that is going to wrap up the video for today. Again, thank you for watching. Subscribe to my Twitter at aerospace666 at twitter.com. I'll be posting updates on there, cool videos and space news that I see, and any pieces of other space information that might be flying around. So that'll do it for today's video. Thank you all for watching. If you haven't already, click like and subscribe, and I will see you in the next video.